Welcome to lecture 21. We're going to do a bunch of examples today, but as always, announcements, there's a homework due tomorrow, but look at the last bullet. We will spare you a new homework this Friday. You have a midterm to deal with. You know the rules about homework. You turn it in tonight, you get bonus points. We will release all solutions to past work, including homework 7, by the end of lecture on Friday. Almost all of it has been released already. There are some that are still outstanding. There are multiple ed posts now on the midterm, probably more than these. You should have received logistics information. If you have any questions, please go to ed, check out the pinned posts, and if you still have questions, then please email data8@berkeley.edu or ask your GSI. Okay. Goals for this week. We're learning A/B testing, and so you have two samples, sample A and sample B, and you're looking at some difference between them, and you're trying to see whether that reflects a difference in the way the samples were generated, or whether it's just chance because you got two things that were different just randomly. So today we are going to use that idea to complete a discussion that we had started before. We have a randomized control trial. We can do the same test to decide whether it was in fact the treatment that was the cause of the observed difference or not. And then we'll do a bunch of examples, and on Friday we'll give sort of a high-level overview of the entire set of contents. So let me remind you where we are. You have two random samples and you've observed a difference. So this is a good image to have. You have population A, and you really don't know what the distribution is. You have population B, you don't know what the distribution is. What you have is a sample from each population, right? And so in the example that was done, the main example that was done on Monday, you had the population of mothers who were smokers, the population of mothers who were non-smokers, and then you had a random sample of each group. And in that instance, we were looking at the distributions of birth weights of their babies. In the sample, the distributions were different. The question now is why? And there are really two options. One is that in the population, they're different, and the samples are just reflecting a difference in the population. Or in the populations, they're actually the same, but we got, just by chance, two samples that look different. And the A/B test tries to decide between these two hypotheses. It's just an ordinary test of hypotheses, but it's just these particular hypotheses are what are being tested. As always, the alternative can have one of a couple of forms. It could be just that the distributions in the population are different, or that one of them tends to provide bigger values than the other. That depends on the situation. So last time, the key idea was that under the null hypothesis that the distributions in the populations are the same, it doesn't matter which member of your sample is labeled A or B, as long as you keep the counts consistent with your original sample. And therefore, under the null hypothesis, you can generate new samples by simply taking your original one and shuffling the labels, and then comparing the samples generated by shuffling. And we were just about to do this in a situation where we had a randomized control trial, and what was being studied was a treatment for back pain. So we had 31 patients who had agreed to participate in this study, and they were randomized into the treatment group and the control group. And so we had a sample A and a sample B. You're welcome to switch those labels if you wish. The point of the randomization is that when you randomize, then before any treatment or control has been given, the two groups are highly likely to be similar. They're not likely to have systematic differences. And moreover, you can calculate chances for how different they can be at the start. And so if you see a difference between the outcomes of the two groups, that it could be due to chance, or it could be due to the treatment, but you have pretty much ruled out that it could be due to some other systematic difference. And so you can do what you really want to do, which is infer causality once you see the result of the test. And so here we had to be, let me just remind you where we were. So there was a treatment and control group, and they were being given a treatment for back pain. And the participants were labeled 1 if they got better and 0 otherwise. And so the data are arranged with the control group first. I think there are 16 of them, and the treatment group second, there are 15 of them. And within each group, you see the ones first, that is those who got better, and then all the zeros. This is not at all a random arrangement. This is deliberately. And so also for the treatment group, and just running our eyes through the table, it certainly looks like the treatment group was doing better. And so we ran a pivot last time, and we saw that in the control group, which is almost the same size as the treatment group, there's a much larger number of zeros. And if you look at the proportions instead, the treatment group has a higher proportion of ones than the control group. And now I want to remind you that when you have a list of zeros and ones, such as this one, the zeros and ones for the treatment group, then adding up gives you the number of ones, and taking the average gives you the proportion of ones. And that is why when we run a group with np.average here, these numbers are the proportion of people who got better in the treatment group and the proportion of people who got better in the control group. And it just seems to be where it's done, right? The treatment group was doing much better than the control group, except that along comes the data scientist who says, wait a minute, no, the groups were assigned by chance. And in your population of 31 people, there are some people who would have got better anyway if you had done nothing to them, right? So maybe those people got into the treatment group, or more of those people got into the treatment group just by chance. And so now we have to be a little bit clear about what our hypotheses are. The hypotheses are about potential outcomes. So we had discussed this last time. At the start of the experiment, we have to imagine that each person would have some outcome should they get assigned to the treatment group, and some outcome should they get assigned to the control group. The difficulty for us is we are never going to be able to see both of these outcomes for a single patient, because each patient is going to be assigned to exactly one group. So our data are going to look like this. We are going to see the right side of the ticket for the people in the control group and the left side of the ticket for the people in the treatment group. And so our data, going back to the notebook, will look like this. So here are the tickets for each of the 31 people. They have two sides. And for the control group, we get to see the right side, but the left side is unknown. And for the treatment group, we get to see the left side, but the right side is unknown. The hypotheses are about this entire distribution of the 31 right-hand sides versus the entire distribution of the 31 left-hand sides. And what we have is a random sample from each distribution. We have a randomly sampled 15 from the left-hand side and the complementary 16 from the right-hand side. So both of them are random samples. If one is a random sample, then what's left over is also random. So now the hypotheses can be expressed more clearly. They are about all of the 31 potential scores. of the two groups. And the difference between this and the mothers and babies example is that in the case of the mothers and babies examples, in principle, you could have gone to every member of the population and got their outcomes, but here we are never going to get it. It's an abstraction that we're doing. We're imagining the distribution of scores that could have been. And so the null hypothesis says that the distribution of all 31 scores in the two groups, those are the same. The 31 potential control scores and the 31 potential treatment scores have the same distribution. And now at this point, you have to decide what alternative you're going to use. I'm just going to today do the alternative that the treatment actually helped. But I should point out that this is not what is done in medical studies. In medical studies, the hypotheses are set up before any data are taken. And the hypotheses don't prejudge what the outcome might be. So invariably in medical studies, the alternative will be the treatment does something, not that it does good. So I'm going to pause for a second and see if I have our alternative here that the treatment helps, but there is a medical research group that is going to do this analysis, and they say, we're going to test the same null hypothesis, the underlying distributions are the same, versus that they are simply different. What would be different in the two analyses? The difference will be exactly in the test statistic. Yes, whether you use the difference or the distance, right? That is going to be the difference in the two analyses. So with our null and alternative here, it is very natural, I think, to use the proportion in the difference between the proportions. We can take it as treatment minus control as the statistic, and then positive differences favor the null. In the case where you're testing are the two distributions the same or different, you would actually take the absolute value of that difference. You would take the distance, and then large values would favor the alternative. I'm not sure if I misspoke the previous when I just discussed our alternative. If we use the difference proportion, I said favor the null, I should not have. Proportion in the proportion of ones in the treatment group minus proportion of ones in the control group. If that is positive, and definitely, and especially if that's large and positive, it favors the alternative, that the treatment is doing better. When we have an absolute value, then large values favor the alternative. So we're going to stick with this null and alternative. In the textbook, we study the other alternative, so you will have both analyses that you can compare. So now, under the null hypothesis, which is when we are going to simulate our statistic, it doesn't matter which one you call treatment and which one you call control. And so let's just go ahead with our plan here. So the group proportions, this array 0.125 and 0.6 is gotten by doing a dot column of the table that we got by grouping and averaging. And so our observed value of our statistic is 0.6 minus 0.125, which is substantial. Okay. But now the question is, could this have arisen due to chance? So we are going to have to shuffle the labels. And for shuffling the labels, actually, let's just take a look at the original table. Okay. Okay. Can somebody tell me how are we going to shuffle the labels? What are we going to use? We have multiple ways of randomizing. We're going to use table.sample. Yes, quite. So we are going to use rct.sample. What do we need to provide as the arguments? Without replacement. So with replacement equals false. Thank you. That's the way to go. What about the sample size? Why is there no need? Because by default, it samples the same number as there are rows in the table. So it defaults to the length of the table. So, and we do want to shuffle the whole lot. We don't want to leave anybody out. And therefore, we actually, luckily for us, we don't need to specify a sample size. Now we want an array of the shuffled labels. So we are going to do a dot column. And we're going to look at the column group. And those are good because those are where the labels are. Okay, so we run that and we'll put it together in a table. Actually, let me look at the whole table. Okay, so the original labels are here and the original results are here. You can see they were in exactly the same order that you saw them before, but now look, the labels have gotten shuffled. So we will do our usual thing. We will see if these were the labels, then what proportion in the control group would be ones and what proportion in the treatment group would be one. And so let me remind you of what we got originally. If we shuffle, if we look at the proportions when group is the label, then that's what we had originally. But if we look at the proportion when shuffled label is the label, then we will get something different. Okay, so now you have 47% versus 25%, which is, the difference is smaller now. And so what we're noticing is that if you shuffle the labels, then you don't get the same difference that you got in the in the original sample. And so now, of course, what we want to do is do it over and over again. And so we have to write a function that actually does this operation. All right, that it takes any table and we provide it the label, the name of the table and the label that we want to group by, and it gives us a difference in proportions. So we will confine our analysis to just the result and the group label, and then we will group and take the proportions. And then we will look at the difference between the proportions of ones. Okay, so there is a question. Why do the proportions not add up to 1? Because they are not proportions out of the same thing. This 0.25 says 0.25 of the control group got better. This 47% says 47% of the treatment group got better. But they are proportions taken out of different groups. Okay, so this difference of proportions is the same function that was defined in the last lecture. We called it difference of means, but we're calling it in that lecture, in this lecture, we're calling it proportions because in this case, the means happen to be proportions. So let's just make sure that if we apply this function to our original table, RCT, and to the original grouping, that we get the right difference. We should get 0.475. And that's what we do. This is our difference in the original sample, but now, of course, we can play the game with the randomized labels. And so, as always, we will write a function that creates one simulated difference under the null hypothesis. And so the first thing we do is we shuffle the labels. And then we look at a table that has the original results, but the shuffled labels. And then we return the difference of proportions in this table. And so one simulated difference of proportions, if I run it, I get minus 0.04 as opposed to 0.475. It's about a tenth smaller, all right? If I run it again, minus 0.3. Okay, so these are, I'm not saying a 0.475 here, maybe I will. So what we need to do is to run it multiple times. We're going to run it 20,000 times. As always, you start with an empty array, simulate one difference, and then append it to the array. And this is going to take a little while to chug, because 20,000 times it is permuting 31 labels, grouping, calculating the average, and then taking the difference. You know, when I used to do this in a live lecture, the whole class would at this point hum the Jeopardy tune. So you can do that wherever it is you are. Okay, I have no idea why this is taking so long. Much better. Okay. So I have a question for you. Null hypothesis. The two underlying distributions are the same. Under that hypothesis, we have simulated this, and our observed value is 0.475. How do we decide whether we're going to look to the right of that or to the left of that? Okay, so somebody has said, very good, thank you. Check the alternative hypothesis. So the alternative hypothesis is that the treatment is doing better, and we need to go back and confirm that we're doing treatment minus control, right? That's the difference, right? So positive values, that is towards the right-hand side, will favor the alternative. And so before we have looked at any of the data or before we have looked at the histogram, we know that we're going to look at the point that we got, that is 0.475 or to the right. And so let me run that. So take a look at that. Does that tail area look large to you or small? Just by eye, what would you say? Yeah, it looks pretty small. So without doing a calculation, if you had to decide at this point, are the data consistent with the null, or do they favor the alternative? What would you conclude? Yeah, these data, they look like they're favoring the alternative. If I have to pick one of the two, I'm going to pick the alternative. To calculate the p-value, you go back and remember that your differences are in the array simulated differences, and you want the proportion of those that are greater than the observed difference. So you count, you can also do np.count non-zero here, and then you divide by however many simulated differences you have, and that number is very small. So the conclusion is that based on these data, it's looking like the treatment is doing good. Somebody had asked, can I go over the for loop again? We start by an empty array, and then we say, wait a minute. For 20,000 times, do the following. Call your function one simulated difference of proportions. This will give you one randomly simulated value of the difference under the null hypothesis. Then append that to your array of differences that you're collecting. This is your collection array, put it in the collection array, and then go back, just do that 20,000 times. And so our conclusion now is that the treatment did well. Could I go over how I defined one simulated difference of proportion? So let me answer that question above it first. What is the difference between a randomized controlled trial and an A/B test? A randomized controlled trial is the way you drew the samples. and it is the design of the experiment. The A/B test is the process we are using to make a decision about whether or not the treatment worked. One simulated difference of proportions. So first, we said if we have a table which has a label and a column of ones and zeros, then we wrote a function to that just gave us the difference between the proportions of ones and zeros. And then we generated that table at random by shuffling the labels, and we called our difference of proportion functions on that randomly constructed table. Can you conclude causation from A/B test? Only if the original data were from a randomized controlled trial. Otherwise not, right? Because otherwise you have no way of being confident that there were no systematic differences between the two groups. So this is the, why didn't we use absolute value? This is the discussion we have at the beginning. We looked at the alternative. Yes, so let's go back. The alternative we are using here is that the treatment did well. The alternative that is being used in the textbook is that the treatment just does something, whether good or bad, right? So in that case, they are just testing for difference from that the two distributions are different, not specifying a direction. So therefore they have a distance. Okay. So the conclusion is that our test rejects the null hypothesis that the two underlying distributions are of the potential scores are the same. It favors the conclusion that the treatment actually does something, and this is actually a causal conclusion because we have a randomized control trial. But we have to keep in mind that this conclusion is about those 31 patients who were in the trial. Every time there is a randomized control trial, the conclusion is about the patients who agreed to participate in the trial. Now, of course, we want to broaden the conclusion to other people, but in that case, we have to run bigger trials and more trials. We have to replicate this on a larger scale. And so in the textbook, there is a discussion of the other studies that had been done. How large of a scale is required? Well, enough that the CDC will trust it. How do we know if the study is controlled? You look at the design of the study. You look to see how patients were assigned to the two groups. So there is a very detailed protocol written out for each such study. And the study has to be approved before it's carried out. So the design is stated in enormous detail, and the participants, you have to explain to them what the design is and that they could get the control or they could get the treatment. So this is pretty much the same as A/B testing. Let me tell you what's this. The carrying out the test is the same as A/B testing. The hypotheses are different because these are about potential scores, and the conclusion allows you to conclude causality, which in general you cannot from A/B tests or any test, in fact. The null hypothesis is not a conclusion. It is something that you are postulating. It is a theory that you're putting forward. And so any theory is going to be about the way the data were generated, not the data that you're looking at, because the data you're looking at, you can actually see them, right? The theory is about the unknown. So the null hypothesis is typically a statement about the population and the way in which the sample was drawn. In A/B testing, the conclusion in A/B testing in a randomized controlled trial, the conclusion is only relevant to the people participating in the trial. In A/B testing, when you're drawing two samples from larger populations, the conclusion is relevant to those two populations. The conclusions are not about the sample. The conclusions about the population. In the sample, the two groups were just plain different. One had a proportion of 0.6 and the other had a proportion of 0.125. That's just different. There's no argument about that. Right? The question is about the population from which these were drawn. And these were drawn from populations of 31 potential control scores and 31 potential treatment scores. That is what the question is about. These are all great questions, and I'm very happy to answer this. Should we do another example, which is not necessarily an A/B test, and then we can see? Okay, so I actually have 3 examples. I'll probably get to do one of them, and then I will complete the slides, and the notebook is already complete for the other 2 examples, and you can study those. And ask questions on it. Okay, so what I'm going to do now is I'm going to give you a question that is less clearly posed than, you have a randomized control trial, et cetera, et cetera, et cetera. This was a situation in a class that I taught many years ago. It had 12 sections. And after the exam scores were released, one section was unhappy about their scores. They said their average was too low. And what happens is when a class does badly, they immediately they hold the teachers responsible. And so this poor GSI was being told that they didn't do a good job. And the GSI's position was, well, wait a minute, it could be just chance. So could we decide? I mean, somebody is saying something could have happened by chance. We should be able to decide. So what we're going to do is just look at the data and then see what are reasonable null and alternative hypotheses and see how we could go about testing them. So this is not exactly like something you've done before, but it's certainly there. Okay, so here are the data. There were approximately 360 students in this class, and there were 12 sections. So here you have the label of the section, right? This student was in section 1, this student was in section 2, this student was in section 4, this student was in section 5, etc. And here you have their score on the exam. The exam was out of 25. Somebody did get 25, yes. And the class average was 15 and a half roughly. So what I'd like to do now is organize these data by section. So can you tell me what I have to do to get the number of students in each section? What should I do? Yeah. So if I group by section, then I have the counts in each section, and there were 12 sections and roughly 30 students each. Okay, so the whole issue is about section averages, average scores. So can you tell me what I would do to get the average score in each section? Average what? Group and then average. Thank you. So group by section, and then take the average of the remaining column, which happens to be the score. And you have that. So now for each section, you have the average score. Which section do you think was unhappy? Actually, let me look at the whole thing. Can't answer that. There you go. Which section do you think was unhappy? Section 3 is looking at their scores and going, wait a minute, what's going on here? Okay, now just so that we can organize our data, and just let's look at how we would create a table that has a section column, a count column, and a score average column. What would we do? We would join. So if I want section, count, and score, why don't I start with section counts, because I'm pretty much there already. And then I join. How do I use join? By section, very good. Can somebody tell me what do I join? Next table, which is called, very good. So section averages. And I'll just put in the column by which we should join happens to have the same name, but I'll put it in anyway. And now you have a table with all of the data. Okay. All right. So the issue is section 3. And in this case, the third argument is optional. Yes, because the labels are the same. That's correct. Okay. So the issue is section 3, and section 3 is not a randomly picked section. It is actually the section with the lowest average score. So the students are saying, you know, there's something wrong with this section. These scores are too low. And the GSI is saying, wait, you know, this could just be by chance. And I would like to say, before we move further, that this is a very bold claim on the part of the GSI, because this is not just any section, it's the section with the lowest score, lowest average score. So the GSI is saying that even that could look like a random sample. Okay, so now we have to be very clear about exactly what that claim is and how, what it is claiming and what it is not claiming. Okay. So which one of the two is going to be turned into a null hypothesis? The GSI's position or the student's position? Which one is going to be turned into a null hypothesis? Yes, why the GSI's position and not the student's? Because it says something is happening by chance, right? And you can simulate data under it, exactly. So what is the null hypothesis saying? Is the GSI saying that the students entered the section by chance? They are not saying that. The GSI is perfectly well aware that students choose sections based on their schedule and which section is open. That is not random, right? The GSI is not saying that it's the students in the section that are random. The GSI is rather saying, look at the 27 scores that are in this section. Those scores look like a random sample out of all of the 300 and however many scores there are. Yes, so they're saying that the distribution of the 27 scores in the section looks like a random sample from the population. That is what they're saying. And so that is exactly what we are going to write down. The scores in section 3 are like a, I'm just going to say simple random sample. Somebody remind me what that is. From all 359 scores. What's a simple random sample? Yeah, we have defined it to be a random sample without replacement, right? Because in this case, 27 students are 27 distinct students. Okay, the alternative hypothesis is the student's position. The scores in section 3 are too low. They're saying low, they're specifying a direction. They're not just saying different for the null to be true. Okay, so we have to choose a test statistic that helps us decide between these two hypotheses. What's a simple test statistic that we could use? Okay, so everything, we've had difference, distance. So let's look at TVD. Okay, does the TVD specify a direction? It does not. Does the alternative specify a direction? It does. We are not going to use any distance, right? At best, we are going to use a difference, right? So difference between what and what? A lot of people suggested difference. Means of what? So class average and this section average. Yes, that's what you're saying? All right. So, but the class average is a fixed number, right? So can you tell me an even simpler statistic that we could use? Just the section average, just the section 3 average is a fine statistic to use, because low values of that favor the alternative, right? You are using, if you want to use the section average minus the class average, what is the class average? The class average is this number, 15.493, right? When you draw at random, is that number going to change? Is the class average going to change? It's not going to change. So you're going to be subtracting off a constant. You might as well just look at the class average. You might as well just look at the section average. You don't actually have to use a difference. And so I'm going to choose, just because we are just going to use the just going to use the average. No, we are not going to subtract off the section score. We are comparing to the class average. Okay, so I'm just going to set, in that case, the observed average is whatever average 13.667 that was we observed. And now we are going to simulate one average by doing what? We are going to take the whole table. We are going to randomly sample 27 scores. Somebody tell me why 27? Class size, that was the section 3 size. Yes, that was a section 3 size. We are going to draw a section 3, a simulated section 3 at random. And then we are just going to look at the average score, and that's what we're going to return, right? That's one simulated statistic. And now we are going to do this 50,000 times, just because we can. Do we need to put in 27? Because otherwise we didn't specify the sample size. Somebody explain to me why we need to put in the 27? The 27 is not the length of the table. The table has 360, we're only picking 27. Right? If we don't put in the sample size, we'll get a section of size 359, which we don't want. We want a section of size 27. Okay, so we run the simulation 50,000 times. While it is running, can we have a discussion? We are going to put this number 13.66667 down on the curve that we get. Can you tell me, are we going to look to the left of that or to the right of that? And how do we make this decision? What do we look at to decide? What do we look at to decide? We look at the direction that favors the alternative. The alternative is saying low scores, right? So we look towards the low side. So our simulation has run and boom, that's where we are. Okay, and so now, well, I actually am leaning towards this GSI. You know why? Because they're saying it's like a random sample, and it's kind of, it's a hard call, this one. So what do we do? What do we do? We actually, I mean, by eye, this is a hard call. Should we actually compute the p-value? Okay, so what we are going to do is we are going to compute this proportion, which means our simulated averages were in the array called averages. So we are going to count how many of them were less than or equal to the observed average, and then get a proportion relative to the number of simulations. And 6%. So if we use the standard 5% cutoff, this GSI gets a pass, right? And I actually feel, you know what? Let's give it to them. Yeah, consistent with the null. Consistent with the null, certainly at the 5% level, or using the 5% cutoff. Yes, but you know, you're saying the GSI got lucky. This is so close. But I give props to the GSI. That GSI had the lowest section average. Right? That one, you're having trouble deciding whether it looks like a random sample or not. Even that one looks like a random sample. So let's give it to them. That's fine. Just generically, as a conclusion of the test, the data are consistent with the null. the section average looks, the section looks like a random sample. Is it possible if we ran the simulation again here? Let's run the simulation again. And then keep asking questions, and then we'll see. I did 50,000 simulations just so that we wouldn't be in that situation. So here we go with the new set of simulations. And yeah, 5.78%, something like that. Okay. So I have 4 minutes to go. I want to ask you a question. The test statistic is simply the average of the section. So the point for you guys to notice is that if you have a whole lot of sections, some sections are going to be high and some sections are going to be low just by random chance, right? It's nobody's fault, actually, neither the students nor the GSIs. Yes, it's actually traumatic to have a GSI running the chat here. Yes, edge case, but you know, this was the worst performing section, right? And even there, it's if you use the conventional cutoff, you don't get a significant result. Why do we pick the average score of section 3? Because if it is low, then the data point towards the alternative. So it is a way, it is a number that helps us choose between the null and the alternative. Okay, guys, 3 minutes. Should we run through the null and alternative hypotheses in another example, or do you want to do those just, okay. Right. Okay, so I'm going to give you, this is classic, the taste test. Right, so you've got some soda and they go to a football game and they give everybody their soda and some other soda in unmarked containers. And this is a bad day for super soda because 91 out of 200 tasters preferred super soda. And so now the board of super soda comes in and says, wait a minute, do less people like ours than the rival? What's going on? And the people running the test say, no, don't worry about it. It's just chance. Okay, so we have to set up, so this is the kind of question that appears sort of in the real world. It's not very carefully stated, and we have to make some sense of this. And here, somebody is saying it's just chance. Can you explain to me what you would say here for it's just chance? And I'm going to see if I can get to a point where I can actually, yeah, I can type in here. Somebody tell me what you would say is due to chance. (50-50). 50-50 is a great thing to start with, right? Now they didn't have drunk any sodas at all, that you just toss a coin, right? Heads, you choose super soda, and tails, you choose the other one. The results are like tossing a fair point. This includes a randomness, right? Tossing a fair coin is random. You don't have to say anymore. You could also say it's like drawing randomly from the distribution 0.5, 0.5, or any other way. Okay, what's the alternative hypothesis? People prefer soda. People like the soda. They don't like the soda. Look at the question. Yeah, fewer people like it. Exactly. So you can say the chance of liking less than a half. Okay, what happened here? Why can you not see what I'm typing? Okay, what statistic would you use? You guys love differences. Do you need a difference? Okay, why are people saying distance? Is there a direction in the alternative or not? Okay, just please, 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 before you use the word distance, look at the alternative. Is there a direction or not? Yes, do not use a distance. No absolute values. Proportion of people who like super soda is a great statistic. I'm actually going to go even easier than that. I'm going to use the number of people who like super soda. You can use many statistics, right? But the simplest one to me is just the number who liked super soda. Yeah, the amount of people. That's the simplest one. Okay, so p-value, you're going to start at the observed statistic, look which way. You could use difference, it won't be wrong. Which way? If you use the number who likes super soda, you will look, yes, you will look at 91 and go left. Okay, great. So that calculation is done for you in the notebook. There is another discussion question that is also solved for you in the notebook. Yes, there is actually plenty of discussion already on ED for choosing a test statistic, but I'll link you to the relevant threads, certainly. Okay, I'm going to actually stop recording because you should have leave to go. But if you looked at the difference, you would still look to the